So in the previous video, we discussed the 4 different methods through which you can actually design a control logic circuit. So one by one we'll be seeing through this particular video. And remember that in detail it is not being shown in this video, just a glance of how the basic logic design of all these 4 methods are being seen. Okay, that is what we are going to cover up in this video. So going to the first method, that is one flip-flop per state method. Here in one flip-flop per state method, let me just show you the diagram first. There will be different flip-flops, okay, and each flip-flop depicts a particular state. So one flip-flop can depict only one state. So how many number of flip-flops are there? One flip-flop per state method. So how many flip-flops are there? That many number of states can only be depicted. Okay, a single bit is said to be propagated from one flip-flop to another. So how it works is that why it is called as a one flip-flop per state method is that during a specific state, only any one of these flip-flops will be set. For example, in one state, if this flip-flop, the first flip-flop is set, it means the set in the sense it is 1. So if this flip-flop is 1, the all other flip-flops will be set to 0, or it will be in the clear state. So it is 1, 0, 0 and 0. Now if in the second state, if the second flip-flop is set, that is if it is 1, then the remaining all flip-flops will be 0. That is this flip-flop will be 0, this will be 0 and this will be 0. So that is the reason why it is called as a one flip-flop per state method. Only one single flip-flop will be set and all other flip-flops will be cleared. The disadvantage of this method is that it requires a lot of sequential circuits. That is, it requires maximum number of flip-flops. For example, in this case, using these 4 flip-flops, you can actually show a maximum of 12 states. That is, you require 12, in order to represent 12 states, you can have 4 flip-flops. So you need 4 flip-flops at least. Okay, that is, if you have 3 flip-flops, then you can represent only 8 states. If you have 4 flip-flops, then you can represent a maximum of 16 states. So if you want to depict 12 states, then the maximum count of 4 flip-flops is required. So that is the disadvantage. The disadvantage is that the sequential circuit uses the maximum flip-flops. The maximum number of flip-flops that is required to design this particular circuit. The advantage is that it is obviously a very simple circuit. And how does it work? Okay, so from this particular diagram, you can see that there is a decision logic. This decision logic sets which particular flip-flop needs to be set. Okay, and this is based upon 2 things: the previous state of the flip-flop and also certain other external input conditions. So based upon the external input conditions and based upon the previous state of the flip-flop, the next state of the flip-flop will be considered. So a transition from the present state to the next state is a function of the present Ti, that is 1, and the certain other input conditions. So the next state is manifested when the previous flip-flop is cleared and a new one is set. So if this is set in the first state, in the second state, the next, any of these 3 will be set. Likewise, only one flip-flop is set per state. Okay. And now if you consider the same circuit without these external input conditions, then you can actually convert this circuit into a shifter. It is nothing but you are just converting, or you are just shifting the bits. So initially it was 1, 0, 0 and 0. Then another, this 1 gets propagated to this flip-flop. So it is 0, 1, 0, 0. Now in the next round, again this 1 gets propagated into this third flip-flop. So it is 1, 0, 0 and 0. So it is basically that 1 propagates throughout if there is no external input conditions. In that case, this particular circuit is said to be a shift register, and if the last sequence is connected to, if the last flip-flop is connected to the first flip-flop, then you can convert it into a ring counter also. So this is an example of a ring counter circuit. That is the first flip-flop per state, that is one flip-flop per state circuit can also be called as a ring counter. Now next one is the sequence register and decoder method. This method uses a register to sequence the control states. Let me just show you the diagram. So this is how the sequence control sequence register and decoder method looks like. So here, if you have n flip-flops in that sequence register, then you can create 2 raised to n states and 2 raised to n outputs. Remember, if there are n flip-flops in the sequence register, then 2 raised to n states and 2 raised to n outputs. So this is an example of a sequence register and decoder that can generate 4 outputs or 4 states. So if it is 4 states that is being produced, then the sequence register will have 2 flip-flops, that is 2 raised to 2. That is, it can have 4 states or 4 outputs, right? So here also, the values that control these states, it depends upon the present state of this particular present state of this output, and then also the external input conditions. Okay, so in previous case there was only one decision logic and then one set of flip-flops, but in this method you have a decision logic, you have a sequence register, and you have a decoder. So the sequence register is said to have 2 flip-flops, and the decoder establishes separate output for each state in the register. So it is the function of the decoder to establish a separate output for each state. And the transition to the next state is a function of the present state and the external input condition. Like in the previous method, in which one flip-flop method, you saw that the transition to the next state depends upon the present state and external input condition. So is in this method also, the present state and the external input condition will make the decisions whether to move to which state. Okay, and again this circuit also, if no external input conditions are given, then you can convert this circuit into a counter decoder method. This can be just considered as a counter. So this can also be called as a counter decoder method circuit. Okay, now the next one is a PLA control method. We have seen that PLA control and microprogram, these two are said to be having the not the hardwired component or not the hardwired methods. The previous two are hardwired methods where you have lot of flip-flops or ICs or circuits, and all of them are connected through wires. So in this particular PLA control method, it is an LSI device, that is a large scale integration device that can implement any combinational circuit. It is similar to sequence register and a decoder method with a combinational circuit implemented with a PLA. So this will look like a sequence register and a decoder method with an additional PLA. Okay, this PLA is, with this PLA, it is actually possible to reduce the number of ICs and the number of interconnection wires. So this programmable logic array enables you to avoid that hardwired component in the previous two methods. And this works exactly in the same way as the previous two methods. You have a sequence register connected to the programmable logic array PLA, and based upon the, here also, in order to initiate a micro operation, which all are the things that are required, you need an input from the sequence register and other external input conditions are also required. This input from the sequence register is based upon the present state of the PLA. So here again, the present state is required in order to initiate the micro operation, just in case of the previous other methods. Okay, the PLA outputs determine which micro operation should be initiated depending on the external input condition and the present state of the sequence register. Okay, in this particular example, the sequence register is placed outside the PLA, but in certain other examples or cases, there are cases in which this sequence register or a set of flip-flops and ICs can actually be present inside the PLA itself. So there could be only one single block. Okay, for this particular case, the sequence register is placed outside the PLA. So moving on to the last method, which is microprogram control method. As we all know, microprogram control method and PLA, in order to make any modifications or in order to make any updations, you can just take out the PLA or you can just take out the ROM from the circuit, make the modifications and place back the ROM. So let's see what all are the things to be taken care in case of a microprogram control. The purpose of a control unit is to initiate a set of micro operations in a sequential order. We know that already. At a given time, only certain operations are initiated while others remain idle. That is the reason why in the flip-flop method, only one flip-flop is set and all others are cleared to initiate one single micro operation while all others are being set idle. So the control variables at any given time can be represented in terms of strings of ones and zeros. So if it is 1, 0, 0, 0 means the first flip-flop is set and all others are idle or all others are 0. So that set of string consisting of ones and zeros, it is called as a control word. This control word can be programmed to initiate various components. So this control word, if 1, 0, 0, 0 means to move a component into a particular register, then 0, 1, 0, 0 means maybe to read a particular component from the processor. So all these control words can mean certain micro instructions or micro operations. So they can be programmed to initiate a particular operation. So a control unit whose control variables are stored in a memory, then you call it as a microprogrammed control unit. So a control unit where all these control words are stored inside a memory, that is if 1, 0, 0 depicts a particular micro instruction, 0, 1, 0, 0 depicts a particular micro instructions. All these things, if it is coded and stored inside a memory, then it is called as a microprogrammed control unit, and all these things are basically stored inside a ROM. So whenever you need to make any updations or modifications, you can just take out the ROM, do the modification and place back the ROM. So each control word is called as a micro instruction, and a set of these micro instructions or a sequence of these micro instructions is called as a microprogram. And in more advanced development known as dynamic microprogramming, permits a microprogram to be loaded initially from the computer or from an auxiliary memory. So in dynamic microprogramming, it is an advanced development of this microprogram control unit. It allows actually a microprogram to be loaded from a magnetic disk or from a computer console. So the control unit that uses a dynamic microprogramming is said to have a writable control memory. This is how the circuit diagram of a microprogram control unit looks like. You have a control memory, you have a control address register, and you have a next address generator. This control memory is assumed to be a ROM, and all the informations, all control informations are permanently stored inside the ROM. Okay, the control memory address register. This address register specifies the control word read from the control memory. So this specifies which control word need to be read from the control memory. The word read from the control memory represents a micro instruction. So it could be a micro instruction to perform a move operation or a load operation or a copy operation. It could be anything. So based upon the control address register, it specifies the control word that need to be read from the control memory, and that word will depict any micro instruction. Okay. And while the micro operations are being executed, the next address need to be computed. Okay. So the next address generator circuit is then transferred into control address register to read the next micro instruction. So the function of this next address generator is to generate the next address. While the current address is being read from it, it is the function of the next address generator to generate the next address. For that, it requires the next address information from the control memory and certain other external input conditions. Based upon that, it will generate the next address that need to be generated. It gives to the control address register. This will pass on to the control memory, and from the control memory, that specific control word is read. That control word will be some micro instruction. Okay. So the next instruction is being read. Likewise, in sequence, different micro instructions are being executed in this microprogram control mechanism. So all these 4 mechanisms are being shown here in a glimpse. In detail, how to design this hardwired and this microprogram control and PLA we'll be seeing in the further videos.